Okay, this is a review of what we did in class for Newton's laws of motion for rotation, and also a little bit from the rolling that we'll do, mainly meant for people missing class, or if you want to review this is kind of long, I recommend you just go over your notes if you were there. And so Newton's laws for rotation, we take F equals ma, and we learned about torque, and force and torque are similar, and so I replace force with torque, which is a Greek letter tau, like period, unfortunately, but that's what it is. And I replace mass with inertia and acceleration with angular acceleration. I get sum of the torques equals I alpha. So it is a new equation, but if you know the rotational analogs, you can make sense out of it. And so we're going to learn how to apply this, and it's the exact same thing we did with Newton's law. Newton's second law for objects moving in a line. So we draw the object as simple as possible, draw and label all the forces acting on the object, but now we have to be careful and make sure that we have the force originate at its point of application, and weight vectors start at the center of mass of the object, which will be the center of the object. So if there was something that was round, mg would start from the middle. If it was a stick, mg would start from the middle. So get used to start doing that. Indicate a coordinate system, so we may be putting a x and a y axis, but we also need to put an axis to show which way is positive for rotation. So counterclockwise would be a little twisty arrow like that. We'd say plus, and clockwise, if we want to do it that way, we'd say plus. And so then write Newton's second law for rotation. Some problems will have to also look at it for translation, and then substitute our torques and rotational inertia, unless that's an unknown, and solve for the unknown. So let's demonstrate that. So I have a massless rod, later we'll include its mass, and a piece of clay on the end, and I'm going to let go, and I want to know what is the angular acceleration and what is the linear acceleration of the end. And so what is alpha and what is the acceleration of the end. So this is a sketch, but this can also be my free body diagram. And so mg is here, and there's another force on it after it's released. There's a normal force here, but I'm going to make that the point I sum the torques about, that is the rotation axis. And so the normal force will not have a torque because it has no lever arm. And so we can sum of the torques equal I alpha. Forgot I had all that all ready to go. Look how similar it is. And the torque is mg times L, which would be the length of the meter stick. And the rotational inertia is for a particle. It's mr squared. And so we have m, and then r equals L. So r and L I'm using sort of interchangeably here. You have to be careful with that. And then that can easily solve for alpha, g over L. And then solving for the linear acceleration of the end. A is alpha r, r would be equal to L, so you get g. So a pretty simple one there. And in case you need to see it, I think I have it on video here. How exciting is that? There it goes. And so we solved only for the angular acceleration and the linear acceleration at the beginning. And so after it starts to fall, that changes. And so what would it be at some other point? And so we want to find alpha when it's some angle from the vertical. And so we draw our forces, sum the torques about where the rotation axis is, so the normal force doesn't show up in our torque equation. Write Newton's second law for rotation. And now the torque is, remember, it's only the perpendicular component and to the lever arm. And so that would be this component, and that's got to be theta, right? If this is theta, this is theta. And so it's opposite theta, so mg sine theta times the lever arm. So the only thing different here is we have the sine theta. In the previous problem, theta was 90. So sine of 90 was 1, so we didn't see that. Now you should be able to figure that out. Notice it's less than before. And so the angular acceleration is only g sine theta over L. And so if you get problems where they ask you how fast things are going, maybe when this goes through the bottom, you can't use alpha to figure that out because it's not constant. But they will ask you to figure out alpha, so you have to be careful. And then if we want the linear acceleration at the end, we just multiply the radius, which would be L, and we get g sine theta. Now that's the tangential acceleration. So you do have to be careful with that. And let's see it.
Here, what would be the acceleration?
How exciting. And so remember, this g sine theta is only the acceleration tangent. We're not really worried about centripetal acceleration so much here. We can ask it, but the meter stick isn't going to fall apart from a lack of forces. We don't need to know the tension in the meter stick. Maybe my clay will fall off. And so this would be g sine theta, whereas the centripetal acceleration is in this direction, and that would be v squared of r or omega squared times r. And you should have learned about the parallel axis theorem, and so let's use it to figure out the rotational inertia of a rod about its end. And so the parallel axis theorem says the rotational inertia of an object is its rotational inertia about its center. Cm stands for center of mass, which for a regular geometric shape, which is all we're considering, is in its geometric center, plus mh squared, and h is the distance from the center of the object to the rotation axis. So you need to know this and how to use it. So here's an example. There's a rod of length L, and we're going to rotate it about its end. And so h is the distance from the center to the rotation axis. So h is L over 2. And so for a rod about its end, it's about the center, 1/12 ml squared, which is given, plus mh squared, where h is L over 2. You can see that'll simplify. We can combine those two and get 1/3, and get 1/3 ml squared. And so you should be able to use the parallel axis theorem to find the rotational inertia of a rod about any point. And the key thing is what the h is h. And so once you know that, then you just apply this formula, and you've got it. We'll see another example later. So we have a meter stick free to rotate about one end, and the mass of the meter stick is m, so we've taken the clay off, and we just have the stick, so we're going to use m for the stick. And the key thing here is the weight vector is in the center. It comes from the center of mass. And then we have the normal force, and we're going to sum the torques about that point. Sum of the torques equal I alpha. And the rotational inertia, you could go through and get it again. We just did that. So that's where the 1/3 ml squared comes from. If this was homework, you can just look that up. It's a rod about its end. But you should be able to drive it, and that's good practice. And so some of the torques equal I alpha. So now the torque is mg times L over 2. It's perpendicular to the lever arm, and the lever arm is half the length, because we always draw mg in the center now. And then there's I that we went to all that trouble to get. There's alpha. And so alpha is 3g over 2L. What is the linear acceleration of the end? And so we put in r equals L. So A is alpha r. Put in r equal L. They'll cancel. So I get 3/2 g, 14.7. But do you believe that? I thought the fastest acceleration anything could have was 9.8. And so that seems puzzling. Let's check it out. So here I've taken the meter stick and I put coins on the meter stick every 5 centimeters, starting at 50. And so if the end of the meter stick has an acceleration greater than 9.8, this coin should lose contact. And actually it will, because she's going to hit it with her finger. So watch this coin here too. And so let's take a look. Take a look. Oh, it's not going. Well, you just got to believe me, it works. Let's see if I can boot it up here. If not, I'm not starting over. Bummer. Must have moved the movie file, something's going wrong. And so if it worked, so you have to ask me in class, you would see this coin would have come off, this one, this one, this one, and this one is kind of there. Let's see if I do that right. 6. And so the acceleration is greater than g up to the 67 centimeter mark. And so we can solve for that. And so A is alpha r. We set A equal to g and solve for what r is the acceleration of g. And so r is 2/3 L, 0.67. Sorry about that, but I'm not starting over. And so now let's consider the clay and the meter stick together. So we did clay, forgetting about the meter stick. We took the clay off and did just the meter stick. And so now what is the angular acceleration of the whole thing? And so we have mg. We have another mg. We're going to say they're the same mass. That makes it a little easier. They don't have to be. And some of the torques about the rotation axis. Some of the torques equal I alpha. And so the key thing here is we have two torques. They're both positive. You have to watch it when torques aren't in the same direction. If there was somebody pushing up, there would be a negative torque from that, depending on your coordinate system. And then for I have the I of the ruler, the stick, the rod, whatever you want to call it, and the clay. So you just add them together. Rotational inertia is not negative. You just add them all together, and there's alpha. So it looks like a mess, but things simplify, and you get alpha is 9/8 g over L, and A comes out to 9/8 g. So those are some examples using Newton's laws for rotation. They get a little trickier when we look at systems with multiple objects, and so that's what we'll look at in class. Take a look at the Atwood machine video that's on my website. So now let's talk a little bit about rolling. If a wheel was going by you, rolling by you at constant velocity, what part is moving the fastest? What do you think? Pause, think about it, come up with your answer. Here it is. It was, oh no, I'm not giving you the answer. And so now which part is moving the slowest? So pause it, think about your answer. And now let's see if we can figure it out. And so here we have just, I don't know what happened there. And so here we just have a wheel, it's just spinning. It's not going anywhere, it's just spinning about its center. And then this is a wheel, it's just somebody's moving by, but it's not spinning. It's not, neither of these things are rolling. Then here's a rolling wheel, so it's going by, rolling on the ground. And so what we're going to do is analyze the rolling, split it up into translation and rotation, and then add it together to see what is really happening. So this thing is just sitting here spinning. So that part of the wheel is just going in this direction with some velocity v. And this part of the wheel is going the same speed, but it's going in the other direction, right? It's just sitting there rolling. And then this isn't moving at all. It's just sitting there spinning about the center. And then here, let's look at the same three parts. This one's pretty easy. They're all just going to the right at some velocity v. And then this is the vector sum. So I add these two together. Oh, what do I get? 2v. I add these together. I get v. And I add these together. That's negative v, positive v, 0. And so the bottom is not rolling, is not moving at all. So the point in contact with the surface of a rolling object has 0 velocity. The center is just going the speed of whatever the thing is that's going by. If you hit it with a radar gun, it'd give you the speed. And the top is going the fastest at twice the speed of the center. So the top was the fastest. The bottom is the slowest, slowest meaning it's not moving. So that's kind of a interesting thing about rolling. Read the book. Here's some evidence for that. It's a bicycle wheel rolling by with a long shutter time, and the spokes are most blurry where it's the fastest and most in focus where it's the slowest. And some other evidence here. I put an LED on a cylinder and rolled it down a ramp, and so the LED is flashing 100 times a second. And so you can see, just look at one of the cycles here. The lights are spaced out the most here. That's where the LED was going the fastest on the top, and they're the closest here and here, when it's going the slowest, when it was almost on the bottom, really close. You can also see that the cylinder is speeding up, and so it gets these spaces at the top get more as it goes down, but we're mainly looking at the spacing of one of those arcs. And so now we're going to look at one of the hardest things that you get asked to do all year, and that is to calculate the acceleration of a rolling object. And this is pretty typical. They'll tell you what the answer is, and you have to show why that is the answer. So obviously memorizing these will not help you. And so it's a hollow cylinder rolling down a ramp, and so you have to learn how to do a free body diagram of an object rolling, in this case rolling down a ramp. And so practice it. Watching me does not help you. It just gives you enough information to practice. So I'm going to put a little dot at the center and at the contact point. At the center and the contact point. And so I know there's a normal force coming from the contact point, and it goes right through the center. I'll draw it really big. And I know there's an mg coming right from the center. And then if there wasn't friction, this thing would not be rolling. I know there's friction, and friction is opposite to the direction it's rolling, and it is static friction. It's rolling without slipping, like we talked about before. And in this case, I'm going to sum the torques about the center. So there's my coordinate system. And so the mg does not have a torque, because it has no lever arm. The normal force, no torque, because it's parallel to the lever arm. It's got a lever arm, all right. It'd be the radius, right? But it's parallel. If you push on something right through the axis like that, it won't make it spin. Friction is the only thing with a torque, and I made it positive, so it's just friction times the radius. The rotational inertia of a hollow cylinder is mr squared, and A is alpha r, so alpha is A over r. Put that in there, and it simplifies greatly, but I'm kind of stuck. That didn't really help me. It says friction is ma, and that sort of makes sense. Kind of reminds me of Newton's second law, and so that's what we need to do here. We also need to write our coordinate system for the y and the x, and use Newton's second law, not for rotation, just for translation, to get another equation. So sum of the forces in the x equals ma, and so I get mg sine theta. That would be the component of mg in the x, positive x direction, minus friction equals ma. And so I have these two equations. I can put that into there and solve for a 1/2 g sine theta. And so practice is the only way to learn this. If this made sense, then you're not paying attention. No, really, this is a tough thing for students. And so I solve this by summing the torques about the center. Later we'll see an example where I'm going to sum the torques about the contact point too. That's another way to do it. I'd say most students like to do it this way. I like to do it the other way, so we look at both. And so how can we do that? Well, there's another way to think about rolling. Instead of breaking it apart into its translation and pure rotation parts, we think of it as pure rotation. So we already looked at for a spinning wheel that's just sitting there, we have V, and we have V, and then V equals 0 in the middle. And then for a translating wheel, we just had V, whoops, well, that's working too. But what about a point here? Well, it would have a velocity like that, and here it would have a velocity like this. And so if we add them as two vectors, remember tip to tail? So I draw this vector, then I draw this one. It's tail starting at the head of this one in the same direction. This would be their combined vector. So this part of the wheel is actually going down a little bit. In this picture, which comes out of your book, which hopefully you've been opening lately, shows you the direction of each particle, each part of this rotating wheel. And so you get the sense that it's trying to rotate about the contact point. It can't because this gets in the way. But if you watch something roll off the edge of something, you will see it start to rotate about that point before it falls. And so this is just another way to think about rotation. You don't have to. It's a complementary way of thinking about it. Read your book. And so here's another parallel axis theorem problem. Pause it, see if you can do it. Okay, we're back. Parallel axis theorem tells me that the rotational inertia is a rotational inertia about the center of mass plus mh squared. And so we're looking at a hollow sphere. I think we're going to have it rolling down a ramp pretty soon. And we're thinking about it rotating about the contact point. And so about its center is 2/3 mr squared. And then h is the distance from the center to the rotation axis. That's just the radius. And so we add an mr squared, and so that's where we get the 5/3. Practice that for other shapes. So now we're going to use that idea to show what the acceleration of a hollow sphere is. And so there's our free body diagram. Pause this, see if you can draw it based on the example I did. Okay, we're back. Remember, I like to mark the center and the contact point. The center and the contact point. I know the normal force comes from the contact point, goes right through the center. I know mg starts at the center and goes down. And I know friction is opposite to the direction it's rolling. And this time I'm going to sum the torques about the contact point. And so sum of the torques equal I alpha. So does friction have a torque? No. No lever arm. Does the normal force have a torque? No. No lever arm. The only thing with a torque now is the weight. And it's not perpendicular to the lever arm. And so it's mg sine theta, it's opposite theta. It's the perpendicular component times the radius equals I alpha. And we just did this. That's using the parallel axis theorem to get I. And so that's the key thing between what I did before, what I'm doing now. I need to use parallel axis theorem to get I for this problem because I'm saying it's trying to rotate about the contact point, not the center. So that makes this a little harder. And this torque was a little harder. But look what happens. I'm pretty much done. And so all I have to do is put I into here, and then I put alpha as A over R, and the M's go, and that R goes, and that R goes, and I get 3/5 G sine theta. So I like this because I just have to do one thing. I need to know the parallel axis theorem anyway, so this gives me practice of it. And figuring out this torque is something else you should already know how to do. And so this is a way to consider trying. So you might try doing this one, summing the torques about the center, and trying the other example I did, summing the torques about the contact point, and get good at both. That'd be a good idea. The end.